What I wanted to talk about here in this video is I want to look at something called transformation matrices. Now, what this is using a matrix upon a two-dimensional system to have some sort of an effect on a point and transform it within that system so that we can then generate either new points or take a set of points and generate some sort of new image based on these using the exact same transformation, such that we can essentially move a diagram around a system and reposition it. Now, the basic idea and premise of this comes from the fact that an object can be drawn by joining lists of points which are defined using coordinates in a fixed order. Now, computers accomplish animations by transforming each point according to some rule and redrawing the object. So the computer animations you see in films, movies, TV, etc., this is the basic premise they are based on. They've got a set of points joined in a certain order, then they use computers, programs and matrix multiplication to move these objects even a tiny wee bit, rejoin the dots in that same order and then get a new image. This helps form the full image that we're after and makes this transformation possible. Now, by performing these in a two-dimensional screens, all of the modelling on the XY plane can be done, and that's what we're going to look at. So these are done as linear transformations. Now, there's a couple of different ways that we can transform points within our system. The linear transformation, this can be described as the mapping of any form where we've got a point xy and that moves to some coordinate ax plus by, cx plus dy. So it's mapped upon there. So we're going to call that x dash y dash. So if we let x dash equals the ax plus by, so the transformation in x, y dash equals cx plus dy, being the transformation in y, then the matrix containing those points that we've now transferred to is the equivalent of ax plus by, so we move the x coordinate along and up a certain amount, and then the y dash would be the y coordinate of the new system, which is the equivalent of cx plus dy, so some movement along the x and then up the y. What we're able to do is if we take this second matrix here, so this matrix which describes the actual transformation, we can split that up and take our original point, the xy, written in column matrix form, and do a matrix multiplication with this matrix here, the ABCD, which describes the transformation that we are doing, do this matrix multiplication, and we get this new image. Now, the position vector of P dash, that's obtained by pre-multiplying the position vector of P by the matrix ABCD. So P dashed is the image, it's the new point that we're after. The original point of the transformation is P, which is the XY. What we do is we say that this matrix ABCD is the matrix associated with the transformation of XY to that new point, AX plus BY, CX plus DY. So that matrix is associated with the transformation. Now, there are three different types of transformations that we can do within our system. One's a rotation, another one's a reflection in some sort of line, and the third one is what's called a dilation or scaling. So we can move the points by scaling them up or down with respect to other areas. So we're going to quickly talk about all three of these in this video and how we can come up with the matrices associated with these different transformations. So let's start in the most basic of terms. Let's imagine I've got a triangle and it's got vertices given at O, which is 0, 0, the point A, which is given by 2, 5, so there's my point A there, and the point B given by 4, 0 there. Let's imagine I want to investigate the transformation given by that matrix there. So I want to know what the image under that transformation associated with this matrix here is. So what I'd do for this is I'm going to set up a matrix which represents all of my coordinates. So if I set up a matrix that has my first point, the O, my second point A, which is 2, 5, and my third point B, which is 4, 0. So if I set that up as a 2 by 3 matrix, I know, given the matrix dimension and the fact that this is a 2 by 2 matrix, I can validly do matrix multiplication on these in order to scale each of these in some way and then use them again to represent my new set of points, so the x dash y dash associated with the O, the A and the B, such that I can get a new point which will tell me how I've modified the coordinates of that triangle. So if I was to do my matrix multiplication, so the usual step, my rows and my columns all together, what I would end up getting is 0, 0, I'd have 9, 10, and I'd have 8, 0. So what that means is my point O remains at 0, 0. The origin under any transformation just remains as the origin. My point A, that's now moved to the coordinate 9, 10. So my point A now, under this transformation, it has coordinate 9, 10. So let's call it A dashed to imply that it's the transformed point A. So I'll go along 9, I'll go up 10. That there is now where my A dashed is. I can then look at this transformation here, and I know then that my transformed point B, so let's call it B dashed, is now at the coordinate 8, 0. So my B dashed is now there. So if I were to join these points up in the same order, O, A, B, what I'd end up getting, if I was to use straight lines, obviously, is a triangle that now looks like that. So what I've done is I've taken that transformation and I've changed the image according to that matrix and moved the points. This is the scaling. So this is the dilation variation of scaling. What I've done is I've taken a matrix and I've essentially multiplied each of the points by this matrix, and it has given me how the points have moved. So I've scaled it in terms of x and y each time, and I can then move it there. So this is the generic one if we're scaling the points according to x and y. If I had a scaling matrix of something, let's call it mu 0, 0, lambda, this would scale a point according to just x or according to just y. So this would take any point, and if I multiplied any point, let's call it x, y there, what I would end up getting for this one is I'd get mu x and I'd get lambda y for my new coordinate. So in terms of that, I would just be scaling with respect to x and y. If I have non-zero values here, my new coordinate for x would be a combination of a scale of the x and the y. My new coordinate for y would also be a combination of a scalar for x and y itself. Now when we're constructing a transformation matrix, there's a couple of ways that we can do it. So first thing is I can consider the image of the point 1, 0 and the point 0, 1 under the transformation, which we're going to define as ABCD. What that means is I can then figure out how those points have transformed with respect to x and with respect to y, and I can take that transformation and apply it to any point within my system, such that I can then do the exact same transformation accordingly. So the point 1, 0, it's now got an image of AC, and the point 0, 1 has an image of BD. So it's transformed those according to those values into those positions. Now, all I need to do is find the images of 1, 0 and 0, 1 under the transformation, and I get the matrix associated with that particular transformation for that system. However, there are times when we don't have that. There are times when we don't have the coordinates of the x and the y intercepts. What would we do under those circumstances? Well, under those circumstances, if we cannot get those, the image of any 2 points allows us to deduce the corresponding transformation matrix. So that would be given by this here. So if we've got any 2 points, x1, y1 and x2, y2, what we can then do is use this to determine the transformation matrix. So what we're going to do is let x1, y1 transform to big X1, big Y1, and x2, y2 transform to big X2, y2, under this transformation defined by the ABCD. What I then know is multiplying these two matrices together gives me this set of system, which is my coordinates. For to do matrix multiplication, I would end up with this system equals that, and then equating the corresponding terms. So I could equate this to x1, this to x2, this to y1, this to y2. What I then get is a system of equations where if I solve them for A, B, C, and D, I'm able to determine the transformation matrix. So I can do 2 generic points as well if I'm not able to get the images of 1, 0 and 0, 1 within the system. So in essence, we need 2 points. It's easiest with the x and y intercepts, but if we don't have them, we can do it with any 2 generic points that exist within our system and that transformation matrix applies to every single point that exists. Let's imagine I ask you to find R, which is the matrix associated with reflection in the line y equals negative x, and then I want you to calculate the coordinates of the typical point P of x, y. So what this would mean is you can imagine I've got a system there where there's my line y equals negative x. And what I'm going to do is come up with a system that reflects in that. So what that means, if I even use basic geometry on a 2D system, I know that with reflection in the y equals negative x line here, a point at 0, 1, will go to negative 1, 0. And I know that the point here at 1, 0, that's going to reflect over to 0, negative 1. So if I then think back to what I had before, my matrix ABCD times the transformation matrix there, what I can tell you is from this first coordinate here, in that transformation matrix, A would be equal to 0, because I've taken the y1 and I've gotten rid of it there, and my C would be equal to negative 1. Using this point here, what I'm able to tell you is that then my B is equal to negative 1, and that D is equal to 0 because of this transformation. So what that then means is that my transformation matrix R, that can be given by 0, negative 1, 0. That will be the matrix associated with reflecting any point in the y equals negative x plane. Now, if I want to get any typical point P of x in this transformation, what I have to do is find my new points, my transform coordinates, so x dash, y dashed, and I know that's going to be given by this transformation matrix here that we just calculated times a typical point x, y. So if I then do that multiplication there, what I'll end up getting is negative y, negative x. So therefore I can say that the image P dashed of the point P is equal to negative y, negative x. So in that system where I'm reflecting in y equals negative x, that's the reflection that will happen. So any point at x, y, this is the coordinate it will go to. So I've calculated that transformation matrix for reflection in the y equals negative x axis, and that's what I do. For any reflection, this is the set of steps we take. We just look at the behaviour with respect to whatever line we're reflecting in. We can also talk about rotation. So I want to find K, the matrix associated with the anticlockwise rotation of theta about the origin O, and then I'm going to get you to calculate the coordinates of the image of a certain point under this rotation. Now what this means is, you could imagine I've taken it here and I've rotated my system theta degrees in the anticlockwise direction. Well, let's look at the points 1, 0 and 0, 1, because if I rotate the 1, 0, 60 degrees, or however many degrees, theta, sorry, I'm going to rotate the 0, 1 the exact same amount of degrees. Now because of that, I can use basic trigonometry here, so my SOHCAHTOA, to determine how far along, how far up each transformation's gone. What that will then give me is my rotation matrix K is equal to cos theta, negative sine theta, cos theta. So that there is the transformation matrix associated with any anti-clockwise rotation about the origin of a set number of degrees theta. So for example, if I took P for part B and it was 2, 4, and I'm rotating at 60 degrees, I'd have my x dash, y dash to my new point. That would be the equivalent of cos 60, negative sine 60, sine 60, cos 60, multiplying that original point as a column matrix, 2, 4. And if I were to calculate that out, that would then give me 1 take away 2 root 3, and then root 3 plus 2. So that would be the coordinate of my new point, P dashed, which is 1 minus 2 root 3 plus 2. So there you go. That's a rotation matrix about the origin. That's how we calculate them.